Welcome to the channel. In this video, we are going to talk about least squares regression. If you've heard about regression, it is basically trying to manipulate a couple of points in a plane with a straight line or a curve. In this video, we are focusing on linear regression. So as you can see on this graph, there are a lot of dots, the points in here, and we have their x and y values in this table. So after we plot them on this plane, we can see that if we draw a straight line like this, let's call it linear series 1, we are kind of passing through the most points, so that we say we have done a regression for all these data points. If you draw a straight line to manipulate all the points, we call it linear regression. And of course you will be able to draw a polynomial line using different methods, but that's not our focus. Okay, now linear regression, we have data points, as I mentioned, let's say from x1, y1 all the way up to xn, yn, and we know that the final result is close to a polynomial like this, which is linear. Then we also have error for our regression. The error is the actual value yi. I is from 1 all the way to n. So for example, e1 equals to y1, which is the actual value, minus the approximated value, which is a0 plus a1 x1, as you can see here. And of course e2 is y2 minus a0 a1 x2. So that's the meaning of this equation. This is the error, quite easy to understand. But let me show you here. The error can be positive or negative. As for this point, let's say this is y1, and this is the approximated value. So y1 minus the approximated value is a positive number. So for this point, e1, let's say, is positive. But for this, y2 is the actual value, and this point is the approximated value. You can see y2 minus the approximated value, e2 is actually minus. So if we want to know the total error, let's say, you would probably write an equation like this, right? Just sum all the equations together, all the errors together. Then the problem is some of the values like e1, it is positive. Some of the values like e2, it is negative. And when you plus all the way down to en, if your point unfortunately locates on the upper and lower side of the approximated line like this, you will probably get a value that is approximately 0, right? Because you have let's say positive 0.1, negative 0.99, okay, something like that. Then after you sum all the errors together, you will get some number that is close to 0, which is not what we want, because actually every point is having an error, but the total error is close to 0. So this is not ideal case, right? So to avoid this, we will do another equation, which is just simply add a square to the error. So you can see after we add a square here, we turn all the errors positive. Then we do the summation. So now this is, we call it capital S. So capital S is actually the thing we want that reflect the total value of our approximation. It wouldn't be affected by the positive or negative of the errors, right? And here, A0 and A1 are unknowns. The method for us to get A0 and A1 is through S, because after the approximation, what we want is for S to be as small as possible. That is to say, for the error to be as small as possible. So we need to now find A0 and A1 such that S is minimized. Now this is a typical question, because I believe you've encountered a question like this. The question is asking you to calculate the minimum value of y. So what do? You take the derivative, right? You will find the point where the derivative of y is equals to 0. Then this point, the corresponding x, is the value you want where y is reaching maximum or minimum. So this is a typical derivative question. But here, the difference is we have two unknowns, A0 and A1. So what do we do when we have multiple unknowns? Of course, we do partial derivatives. Now, the thing is getting clear. We just let the partial derivative with respects to A0 and A1 equals to 0, right? Then we are hoping to solve these two equations to get the value of A0 and A1. So let's do it. Now for the first equation, we can derive A0n plus this guy and the second equation is xi squared a1 equals to this guy yi. Okay, so yeah, we turn the two simultaneous equations into these two, which is more neat, and then you can use the famous Cramer's rule to solve it. Now, here, these two equations show you the Cramer's rule. Okay, and you can get these two. Okay, now as we can see in these two equations, we have all the summation elements, right? And we also have n. What is n? Let's see. N is the number of points we have, because where did n first appear? Here, right? xn, yn. From x1, y1 all the way to xn, yn, which means we have total n points. So here n means the number of points, and the summation is also not difficult, right? I believe everybody can compute that quickly. So yeah, now you get a0 and a1. We substitute it back to our original equation. Then you have the linear regression of all the points you have. So how do we know the performance or the quality of your regression? We have a term called correlation coefficient, R. And how do you calculate R? R squared is equal to S0 minus S divided by S0. Here, S0 is the summation of the square of the difference of yi minus y bar, and y bar is the average value of all the y's. So actually, if your r square, or if your r is close to 1, the closer it is to 1, we can say the better the quality of your regression. Now let's see an example. For example, we have 5 points, okay? 5 points, x, I, y, I, and I from 1 to 5. And we want to do a linear regression to all the points. So it's just to calculate a0 and a1. We already have the equation. We just you can remember all these stuff, or you can just start all over again, use Cramer's rule to compute it. And since we just derived that, we don't do all of it again. We just substitute all the values here. As you can see, it's quite easy, because this one is just the summation of all these values here, right? And this one is the summation of all these values here, and the others are just much alike, right? xi, yi, you do x1, y1 plus x2, y2 all the way to x5, y5. Yeah. And this one is just x1 squared plus x2 squared all the way to x5 squared. So far so good. And also this one, just be careful, these and this, they are not the same. This one is actually x1 plus x2 all the way to x5 and then square, so be careful. And also you have noticed that n is 5. We have 5 points, right? So after calculation, you will get a0 is equals to minus 0.18, and a1 is equals to 1.06. That's it. Now earlier I have plotted the graph of these 5 points. As you can see here, these are 5 points, and this line is actually y equals to minus 0.18 plus 1.06x. The performance is pretty good, yes. And Okay, if you are unable to plot this, if you don't have a computer or you don't have MATLAB to do that, you can, as we said, compute the correlation coefficient, R. Okay, so pretty simple. R is equals to S0 minus S over S0. So S0 would be yi minus y average. Okay, square. We can quickly derive 11.54, and S is the actual value minus approximated value. To avoid plus minus, we have square, and we have 0.304. Now y bar is actually 3, so R is, just put all the values in it. Pretty good. Really close to 1, as you can see. So from the graph, it is the performance is good, as you can see, right? Now the problem is, you will not be so lucky every time. I mean, you may not have the 5 points like this. They are lined up, okay, pretty perfectly along a straight line. What if you encounter something like this? Let's say this is the 5 points I got from DeepSeek. Okay, I told it to give me something non-linear and to challenge myself. Okay, so yeah, after I plotted using MATLAB, you can see it is, you really can't say that there is some straight line passing through it that can perfectly manipulate the 5 points, right? Because they are just, yeah, they're banded. And actually, if you've noticed, this one is actually something like y equals to ax to the power of b. Maybe maybe y equals to x squared, something like that. So what do we do about that if we want to use the least square regression? Actually, we can transform it back to a linear appearance by simply taking ln on both sides of the equation. So on the left side ln y, and right side ln a plus b ln x. Yeah. And let's say capital Y is equals to ln y. This is capital X. This is capital A. And this is capital B. Then this equation is actually y equals to a plus bx, right? We turn it into a linear form by simply doing ln on both sides. So after we've done that, you can have ln x, ln y, and for this we can actually apply the same method we mentioned again, right? So now the aforementioned method, we calculated a0 and a1. For this, a0 is capital A, right, and a1 is capital B. So we use all the equation we've derived. I won't write it again. You will get a is approximately 2, b is approximately 1.5, right? And your original equation is y equals to ax to the power of b. Now what is the a? Line a equals to capital A, right? So a equals to e to the power of a, which is, oh sorry, now capital A is approximately 0.696, so the a is approximately 2. This is the drawback when you compute all the things earlier and you forget about which is which. Anyway, capital B is just B, right? And it is approximately 1.5. So the final result is 2 times x to the power of 1.5. Now let's quickly check if this is a good result we want. Let's just say shuffle in x equals to 2. Y should be 2 to the power of 0.5, which is, well, 5.656. And what we wanted is 5.66. So we got it. The performance is good. So, yeah. For some of the nonlinear relationships like this, we can do some transformation on the equation and get the same old linear form and then perform what we have. Thank you for watching.